My name is Ranger Kuang, and I researched how we can improve supercapacitors through chemical design. Supercapacitors are a type of portable energy device that are critical in our daily life when everything from your printer to military-grade vehicles require quick and convenient energy. While supercapacitors can charge and discharge energy quickly, they don't perform as well in terms of bulk charge storage. So I wondered, how could we remedy this problem? Well, one conventional way is to increase the surface area of the electrode that can hold charge. Porous activated carbons are a common choice as they boost surface areas by over 1,000 square meters per centimeter squared. Another method is by adding chemical species onto this carbon material. Chemical species can add redox reactions, which can supplement the charge with additional electrons. My project deals with increasing energy densities of supercapacitors by modifying their electrodes with carboxyl and alcohol functional groups. I chose these groups because they have oxygen atoms, which are highly reactive and known to be redox active. Now, the reason why I became fascinated in this project was due to the usage of chemical reactions, not physical transformations, to improve energy storage designs. Furthermore, I want to learn how far we could push these chemical modifications before they fail. So in order to conduct the experiment, I needed to actually make a supercapacitor. So there were three main steps to this. The first step was to deposit the two functional groups onto commercially purchased YP50 activated carbon. After functionalization, an infrared spectroscopy scan, shown in Figure 3, validated the presence of the carboxyl groups. In this example, these two peaks right here validate successful modification. The second step is creating our electrode with the functionalized carbons by pasting them onto a disc-shaped carbon paper substrate. Steps 1 and 2 were provided for by my lab. The third step is to assemble the device by quote-unquote sandwiching an ionic membrane between two electrode disc plates. The ionic membrane provides the free-flowing ions that can flow from one electrode to another during charging and discharging. Now, these were my steps I laid out. However, upon preliminary testing, I found that the pristine supercapacitor itself was not performing nearly as well as I had hoped. Through additional tests of the device's internal resistance, I realized that during the quote-unquote sandwiching process, I was not nearly applying enough force to press all of the parts together, and thus there was no stable connection between the electrode surface and the ionic membrane. This instability was causing high internal resistance, so I had to vary the pressing force and pressing time to find the optimal parameters to have the device pressed enough, but not so much that it caused the device destruction. So, with the devices fabricated and with that roadblock overcome, I performed two tests to evaluate their specific capacitance, calculated by the third formula right here, where M is carbon material mass and C device is found with machine readings, from the second equation. Both tests mimic a practical charge-discharge cycle of the supercapacitor. First, a cyclic voltammetry test was performed, where the voltage of the device was scanned back and forth between plus minus 0.5 volts. Second, a galvanostatic test was done, where instead of choosing a voltage scan, I chose a constant current to charge and discharge the supercapacitor. Figure 5 from our first test shows that at low scan rates, or slow charge cycles, both functional groups completely outperformed the pristine carbon. At the lowest scan rate, the carboxylated carbon saw close to a 3-fold increase, and the alcohol carbon saw a 4-fold increase. However, at higher scan rates, the capacitance of functionalized devices degraded more quickly than their pristine counterparts. Figure 7 from our second test shows a similar trend. At low current densities or slow charge cycles, the functionalized carbons hold more energy, but at high current densities, that boost in performance almost disappears. Both tests suggest that the functional groups are providing redox reactions that boost performance, but the reactions are not fast enough to keep up with very quick charge-discharge cycles, and thus cannot sustainably boost capacitance. In summary, my experiment supports my hypothesis that functionalization of carbon electrodes with carboxyl or alcohol groups can increase the energy densities of supercapacitors. However, I did not expect to see that boost in capacitance almost disappear at quick charge cycles. With enough strain, we are seeing a trade-off. High power output for lower capacitance. This limit to functionalization expands on prior research as it introduces this novel idea that chemical modification is not a blanket solution to improved energy design. Finally, I also wish I could have overcome certain limitations in my research, the largest one being that my functionalization modifications were a fixed change, either functionalization or not. Depositing a larger concentration or lower concentration of functional groups can give us a better understanding of how much we can truly boost capacitance, as well as if the degradation point of our functionalized electrodes changes. In the future, I will try to overcome this limitation, as well as see how functional groups may retain deposited large redox ions onto the surface of the electrode to allow for further redox activity. Thank you.